All right, let's do another one of these programming sessions. We'll call this one number 2. I am still working on programming session number 2. I'm still working on the TKInput class. Last one was a debugging session. This one is not really so much about debugging as implementing some new features. So I fixed most of these bugs. Actually, after I shut off the video from the last session, I did fix a couple more bugs. One of the main ones was I left it off where if you used the left shift key and the right shift key at the same time, that wasn't working. So for example, if you put the cursor at a spot, hold the left shift key, and then you try to cursor up, which requires holding the right shift key and pushing the vertical cursor key, that would fail. And same with if you tried to hold the left shift key to extend a selection and grow your selection towards the right, you had to use, towards the left. So towards the right it would work because you're just using the right cursor key, but towards the left it was not working because you'd have to combine it with the right shift key in order to go leftwards. Okay, so that was not working because the key equivalent event, although it had, although the PETSCII decoded code for the cursor keys was cursor up or cursor left, it also included the flag that indicated that the right shift key was being held down. So I was checking to see only that the left shift key was being held down. But of course, the event captures that both shift keys are being held down. So anyway, minor problem. That's working. So this time what I'm going to do is I'm going to implement a couple things. Let's boot up into C64 OS just to see what it does. I can kind of explain what it does. There are two kinds of keyboard events. There are the keyboard events that are the result of not using a modifier key. And then there are the keyboard events that are the result of using a modifier key. So if, for example, you push, so let's say from the ready prompt, if you push Control and then you push anything, it will actually produce a character in the keyboard buffer that is like, some PETSCII control character. But if you don't use Control and you push some key, maybe even the same key, you still get a byte of PETSCII in the very same keyboard buffer. It does not work that way in C64 OS. Basically, if you use Commodore or Control, you will, you can use them in combination. You can use Commodore and Control, but you have to use either Commodore or Control. And then you can also use that in conjunction with Shift as a third modifier. But if the modifiers Control or Commodore are included, you don't get a PETSCII byte in the keyboard buffer. You get a special, more complex, like multi-byte event, and it goes into a special event queue just for those. However, if you push unmodified keys or keys modified only with Shift, well then that actually populates the standard keyboard buffer that like the regular kernel uses. It doesn't use the kernel's driver, but it populates the same buffer. So what that means though is that cursor keys, they end up, cursor keys, delete, they end up as PETSCII control characters in the regular unmodified key buffer. So what that means is that when you're reading the stream of events out of the standard keyboard buffer, you first have to say, is this byte, is it some sort of a control sequence? So for example, if it's a cursor key, well, you're not going to insert the PETSCII control sequence into the middle of the string. You're going to say, no, that's a control sequence, let's move the cursor. Okay, that's basically what the screen editor does, right? And if it's delete, so we basically search for cursor keys, we search for delete, and so on. So when we just typed 4 letters, that put 4 PETSCII characters into the buffer. But when we hit delete, the delete goes into the buffer, the keyboard buffer, not the string buffer. The delete goes into the keyboard buffer. The delete gets read out of the keyboard buffer by the TKInput class, but it gets interpreted, oh, that's a delete. That's not an insertable character, it's a control sequence. And then it goes off and it does some other code that manipulates the string. Now, what happens if we push clear? So that's unmodified. We hit clear. What do? We get this weird, whatever. This actually starts to look something like, it's not exactly the same, but it looks something like what happens when you capture a PETSCII control code in a quoted string in BASIC. You end up getting these kind of reversed character codes, right? Now, the reason that we can't or don't have to worry about capturing something like, how about the PETSCII code for red, is because the only way to type a PETSCII code for red, typically from the ready prompt, is to use control. But of course in C64 OS, as soon as you use control, you don't get a key just in the buffer. You get you don't get a key in the regular keyboard buffer. You get it in this weird special modifier key events buffer. So, long story, but we have a couple of control characters that we need to support. So I'm going to type Greg, then I'm going to hit home. I'm going to hit shift home. I get clear, okay, so that's clear, but nothing still puts it in there. Or now maybe I'll cursor back and I'll say, oh, well, what about insert? Okay, so that puts in that weird symbol. Now, honestly, I don't know what to do with insert. I'm thinking, maybe in some future version, the TKInput class could support insert versus overwrite modes. Honestly, on the Mac, I don't think I ever use the overwrite mode. I never use it. Overwrite is basically how the C64 works all the time from the ready prompt. But that's just because overwrite is a simpler thing to do. It's more complicated to move data and insert. But, so I think for version 1, I'm going to just ignore the insert code. And then I put out on Twitter what other people think makes sense for home and clear. So for home, I'm thinking really that should just do the equivalent of cursor up, which moves the cursor back to the home position of this field. And clear should, I think, clear the whole field. Now, it's a bit destructive. Some people thought, well, maybe instead of clear, it should be the same as select all. But then I think, well, we already have select all, so fuck that thing again. Actually, I have an explanation for that. Let us derail for 2 seconds. So I think I said in my previous video that it was like my jittery fingers. But what I discovered is this may actually be kind of a bug in the way the keyboard driver in C64 OS works. So what happens here is if I hold Commodore and I push A, and now I release A, and now I release Commodore, okay, you've got no problem. But watch what happens if I hold Commodore, push A, but then as I lift up my fingers together, imagine now that I accidentally lift up the Commodore key just a little bit before I lift up the A key. Well, that would mean that the A key is now depressed unmodified. And so here I'll do that. Boom. And there you go. That's the problem. You see, so all I've done is I've lifted the Commodore key kind of first, and the A key last. And the keyboard driver has picked up that depressed A as though I had pushed A. So I actually should try and fix that, but it's a much lower level bug in the keyboard driver. It's nothing to do with the TKInput. Anyway, some people think that I should make clear just do a select all, but yeah, I don't know. I'm leaning towards making clear actually clear. Okay, I made another note of one other feature I would like to implement, and this comes from macOS. So I always thought it was very clever that in macOS, and Windows I think did not do this, and I thought Windows was kind of stupid for this, and I thought macOS was clever. So, because I'm a Mac fan and I like clever things, I think I'm going to implement this. So basically what it is hiding the mouse cursor when you start to edit text. Now the reason for that is because let's say that I click on this field and there's my mouse right there, okay? And now I type greg, and lo and behold, what is the mouse cursor? The mouse cursor is exactly where I left it, and it's exactly where I don't want it to be. It's obscuring the content that I'm typing in. So this happens to be test ground, and so I actually have tests here for testing the various features of the mouse. So we have kill. Each of these menu options here calls something in the kernel that's available for the mouse. So kill basically shuts the mouse off completely, and basically the kernel stops polling the mouse altogether, like it's off. So that would be useful for like games and stuff, right? And you could programmatically kill it, and you could programmatically turn it back on. Hide, however, is what I want to do. So watch what happens. Okay. Before I actually show this to you, I'll just explain these. So hide simply causes the pointer sprite to be turned off, but everything else about the mouse scanning system is still totally active. Show is just the opposite of hide. It just programmatically flips the sprite back on. Load is effectively the opposite of kill. So if it's killed, load will load, but load has the load also actually reloads the sprite, the mouse sprite and colors, I think, from the selected mouse pointer settings that you have. So it loads the mouse pointer sprite in from disk. The reason I did that is because I assume if you're going to use kill, it's probably because you're going to implement a game. If you're going to implement a game, you want to be able to have access to all the sprites, in which case you're probably going to overwrite the mouse cursor sprite, in which case when you load, you gotta re-establish the mouse pointer sprite. So now let's test some of these out. So watch, if I hit Commodore H, okay, sprite is gone, but if I simply touch the mouse, boom, it's instantly back. So you see it's still active, it's just, and it auto unhides it, right? Which is exactly what macOS does. So hide, and then as soon as you want to use it, it's just, oh, well, there it is. You see? But if it's here, and it's hidden, and now, another moth, and now, go away. Okay. Oh, there it is. Fruit fly. Anyway, and now all of a sudden, it's not in the way of the field, but I wiggle the mouse and boom, it's right back. So I'm going to implement that too. Okay, let's get out of here. Actually, something I was thinking about, that whole video I made last time, I don't think I ever reset my Commodore 128. And I just wanted to point that out. I thought it was kind of cool. I can go into the assembler, I can drop to basic, run some basic tools, go back into the assembler, assemble something, boot into C64 OS, drop it to C64 OS, go into the assembler, and so on. And I never actually hit the reset button on the machine, nor do I power cycle it. Alright, let's go into our toolkit directory. We're going to run Turbo Macro Pro, which is in the root directory. And we're going to load in TKInput.a. Okay, so once again, here's our jump table. We've got our do key equivalent. And we've got our key press. So key press is being called by the toolkit environment when there is a regular unmodified key waiting in the buffer. So that's what our home and our clear and our insert are going to be. So let's jump there. Let's go back I for find label. Key press. Okay, so we call our kernel routine. Call our kernel, make our kernel call to fetch the next key in the buffer. Now, if you're actually polling the buffer, you could poll the buffer with this routine, and the status of the carry will tell you whether the poll resulted in finding a character that was buffered or not. So the carry, I think, if the carry is clear, the accumulator holds the character. If the carry is set, the accumulator is nonsense, and there was no event found. Now, but in this particular context, inside the toolkit, key press is simply never gets called by higher, like key press gets called when it gets called by higher level processes in the toolkit kernel module. And if there isn't a key event waiting, key press is not being called on objects. So you don't have to, whenever the key press event, whenever the key press method rather is called on an object, there is a key waiting. So we can just immediately start checking for it. So so what I was saying is exactly what's going on here. We've pulled a key. It could be the letter A or the letter G, or it could be it could be delete. So we basically do some checks for the various types of control characters. So we have cursor up. I've got a note here that takes you home. It's not actually the home, but it takes you home. And I've got cursor down, I got cursor left, I got cursor right, I got delete, I've got return. Yeah, return actually, return is a special kind of control character. I mean, if this was a multi-line text input, okay, it would be added to the string. But because this is a single line editor, return is interpreted as a control sequence, and what it does is, because the TKInput class is a subclass of TKControl, TKControl can be assigned an action, and an action consists of either a static routine to be called, or it can be assigned a pointer to an object with a method offset on the object. It's got a few different options like that. It has a couple more complex, slightly more complex things too that I also pulled from macOS, although it's nowhere near as sophisticated as the way the macOS frameworks distribute events. But yeah, in this case, if you push return, it will attempt, I mean, actually you can see it right here, it calls send act on this. And then from there, well, it's based on the way TKControl handles actions. Okay, and finally, if it's not one of these known control sequences, it just falls through into insert character. Okay. So, the easiest, really, would be, since cursor up already has this note that it does home, we should just support home right here, right? Okay, so to know what home is, we go back to our complete interspace anthology. So control, very early on, I got right into PETSCII, and I actually like PETSCII more than ASCII. I got to admit, ASCII is based on a 7-bit code where everything is packed into, I call them blocks. So in my opinion, there are 8 blocks. You have 1, 2, 3, 4, actually 0, 1, 2, 3, 4, 5, 6, 7. ASCII is 7-bit, so it's only this page, and it basically is controls, numbers and symbols, uppercase, I think, and then lowercase, I think I've got that right. Uppercase and then lowercase. PETSCII is an 8-bit code because it was written in the days of personal computers and not teletype machines. And so PETSCII has codes. Okay, actually, what it has is these. This is a lesson in PETSCII here, folks. These upper blocks, say, of PETSCII, they all have their high bit set, right? Bit 7 is set for all of these. And besides bit 7 being set, they're a perfect mirror of these. And from the ready prompt, when you push a key, if you hold shift and push a key, it will, like if you hold A, it'll put in, say, 65 in decimal, or 41 in hex. But if you hold shift and hit A, the only thing that does is it produces the exact same character but with the high bit set. And so the uppercase version of the lowercase letter is this block, this mirrored block over here, but with the high bit set. So what's kind of neat about that is that where ASCII has this 0 block for codes, PETSCII also has this block for codes. And what's kind of neat is keys that have two functions. So you have the run stop key. So you have stop, but if you hold shift, you have run. So here you have 03 is stop, but when you hit shift and the stop key, all it does is set the high. So 83 is run, right? Same with the things like switching between text mode and graphics mode. So text mode is OE, but the shifted version of that is 8E, right? Same with reverse on and reverse off. So reverse on is 12, reverse off is 92. And so why are we here? We're here for cursor home and for insert. No, clear. Yeah? Yeah. So cursor home is 13. Clear, that's the shifted version of the same key, is 93. Right? Just sets the high. Shift just sets the high bit. Delete is 14. Insert's 94. So let's start with home. So that'll be 13. That's 13 in hex. 13 in hex. Now, we are just going to use the exact same implementation as cursor up. So what that means is that, okay, in all of these previous implementations, it's been one check, and if it's not that check, skip to the next check. Check one character. If it's not that check, skip to the next check. In this case, though, we've got two characters that do exactly the same thing. So the implementation is a little different. It's actually easier. So we'll go, in this case, we're going to say, if it is 13, then we're going to branch into the implementation for cursor up. But if it's not 13, well, then that will fall immediately through to the second check for the same implementation, and that will work. In which case, I don't have to mess around with this at all. So we're going to say, okay, compare 13. Yeah, hex 13. And if it's equal, here's an example where there's no way in hell I can sacrifice a label for this. You know, I mean, just to go from here to here, it's just, I can't justify a label. Besides which, I actually feel like it kind of pollutes the space. So we just count the bytes. 0, 1, 2, 3, 4, 5, 6. Boom. That, I swear to God, is it. Now we've supported home. Home should now send the cursor to the start of the field. Isn't that great? Okay. Okay. Clear will be a little bit more complicated. I don't think we can just back end on something else, because there's nothing else quite that does clear in one step, right? Now end, I mean, if we had an end button, we could implement end, but the Commodore 64 keyboard doesn't have an end key, which is what cursor down, that's the whole point of cursor down, right? Because there's no end key. Okay, what else we got here? Cursor left, cursor right. Okay. Where's my pencil? So what did we just do? We did home. Okay, insert. Yeah. I'm going to stick insert right here just before delete. Okay. Yeah, so somebody asked on Twitter about, no, actually they didn't quite. Somebody asked on Twitter, or said on Twitter that I should use labels for my relative jumps. Like, so for example, this relative jump. Somebody said, yeah, you know, if you're gonna make a relative jump, you know, you should put a label, you should put a comment here at least that says where it's gonna go. But I'll just say that my typical technique is that I only use the relative jumps for short jumps. And I tend to put spaces between sort of logical units of code. So this 12, let's just see where this 12 goes. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So this is a typical pattern for me. The branch to 12, it goes to the next block. It's like, if it's going to go forward, not plus is going to go down the code, minus would go up the code. If it's going to go down the code, you know, I'm not going to have it go to here. That would just be weird. The point of these spaces here is to say, you know, this is just skipping this block. Okay? Anyway, but then another example is I also said I don't use relative branches for, you know, these huge complex jumps. So this is an example of a this is a pretty good example right here. What am I trying to say? So like, let's say here, this jump here, it's really just gonna go down to here. I mean, I don't really need to put a label. I know it's gonna go down to here because, again, I've got these spaces around this code, and I just know that this is a unit, and this branch is not destined to just fall into the middle of this unit. It's designed to jump over the unit, okay? But when we get down to, say, cursoring left, where, oh, now all of a sudden that's more complicated. It's got these relative branches inside it, and it's, you know, and it's quite long. It's longer than the length of the screen. Well, I use a label for that, right? I mean, I'm not opposed to using labels. It's just I have to be judicious about my use of labels. So there's an example of using a label when it's a complex sort of distance jump. How about this one here, just for fun, right? My 20 looks too short to get just to here, so my guess is 20 is going to get where? To here, maybe? I'm not sure. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, I messed up. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, so in this case, that 20, it is skipping both of these. Okay, call me inconsistent. Somehow it makes sense to my mind. All right, where were we? Okay, insert. So insert, what was insert again? Insert is a shift of delete, so 14 would be 94. Insert is 94. I'm putting insert and delete side by side so that 94 and 14 are right side by side. 94. Now, if it is a 94, I don't want to do anything. I just want to get out of here. So I'm going to branch to done. Done's just an RTS. Okay. So push branch to done. I think I'll put a comment on that, right? Now our inserts. Okay, so that's going to do insert for now. All right, how about clear? Yeah, okay. So clear is a little bit more complicated, right? Basically, clear has to consist of clear is going to set the insert index at 0. It's going to set the anchor at string length. It's going to call delete range. And then I think I don't think there's anything else to do with that. That'll readjust anchor to be 0, and it'll mark as dirty and all that stuff to redraw. And it'll track the cursor automatically. So if we go to del range, for example, yeah. So the other thing I was thinking, well, maybe I shouldn't. Maybe I should do a check to make sure that the string is actually more than 0 bytes long before doing that. But now that I'm here, I think, okay, well, maybe delete range actually handles what happens if you call del range on a 0 length string. I'm not sure. So if the index is less than anchor, but it will not be, so let us just branch down to here. So if index is greater than anchor, now it actually just assumes that index is greater than anchor here. Yeah. So basically, del range assumes that the string is greater than 0 characters, which is why in the previous video, when you hit delete, I was explicitly checking to make sure that the insertion index is greater than 0. And that solved 2 problems, right? Because it solves the problem where the cursor's just at the beginning of a string. You have a bunch of characters, the cursor's at the beginning, and you hit delete. But it also solves the problem of if the string is 0 length, well, then your insertion point is at 0. And so anyway, we'll have to, in clear, we're going to have to check to make sure the string is actually greater than 0. Okay. And then if the delete range actually works, it's going to jump down here to done. It's going to do the actual string deletion, and then you see it. So after manipulating the string and changing the index pointers and all that stuff, which we went over in the last video, it automatically falls through to the insertion point tracking, which is something I have to improve. So all that means is that if the text field has way more text than can fit in the field, or than can be seen at once, and your cursor is way down here somewhere, and so the field is scrolled, if you hit clear, it will track the insertion point, and it'll put it back where it's supposed to be. All right. Okay, let's go up here to all right, maybe we'll put it right before insert. Clear. What's clear again? Sorry. Clear is 93. Clear is 93. Alright, so if it's not 93, here's another little trick I use. If clear is not equal to 93, I'm going to do a relative jump for now, right? This is just, I don't know, maybe I'll need a label. If there's going to be a crap ton of code in there, okay, maybe I'll need a label. But for now, I'm going to do a relative jump. Problem is, I have no idea how much code's going to be in there, so how far am I going to relative jump? So here's what I do. I pop in an FF just because I just always put an FF if that is not a valid jump. So if I ever see a star plus FF as a jump, it's like, whoa, that's not a valid jump. You know, I haven't dealt with that. And then typically what I do is I put a temp label in all caps. This is a standard for me personally. The reason I do that is because I might navigate away from this, right? I mean, I might get confused and start working on something else up here, and then I might think, oh, did I finish everything I was working on? I don't know. So what I do is I search for temp. And if I find any temp in the file, I mean, it just brings me right back to something I need to do. Basically, because this FF is literally not right, but I've typed it in, I put temp because it tells me it's an anchor point for something I need to update. Okay. All right. So what are we gonna do? So the first thing to do would be if the string length is 0, clear will do nothing. We can just branch to done. So we're gonna load. Now I actually go. I didn't show this the last time, but here is my binder with all of the notes for all the classes. So what I have, these are the methods. TKInput, believe it or not, has no methods. They're all just TK control methods. These are the properties, custom properties that are extending the properties of TK control. So a TKInput has all of TK control's properties, but then it has these as well. And then these are notes on how the delegate methods get called. And then I have other notes around here about the logic for insertions and tracking the insertion pointer and all that kind of fun stuff. So these are the property. These are the properties. So what am I looking for? ISTRLen is going to be the string length. So ISTRLen. LDA this. So we're object-oriented programming here. So basically, whenever a routine is being executed, but that routine is actually or conceptually a method of an object, this is set, and this should be this. So this is a routine, but I can just use this, right? As the pointer. This is so it actually kind of feels like object-oriented programming. So yeah, so basically, like, when I look up the ISTR length on this, it's like I could have 5 different text inputs or more on the screen, and but which one am I actually, whose data am I actually working on? The method doesn't care. It's just working on this's, right? So that this pointer will be the right instance for this to work on. So it very much is object-oriented. What do we got for time here? 45 minutes. Talking too much. All right. So we're just going to check the str length, and if it's 0, we'll get the hell out of here. Okay. And otherwise, we're going to load A with 0, because that's going to be our insertion index. So I index, I anchor are the next 2 properties. No, actually I got a better idea. I got a better idea. Here's what we're going to do. So we've just loaded our stir length, right? Stirlen. So that's where we want the anchor to be. So we'll load y with the I anchor, and we'll store that at this. So we've just loaded the stir length. If it's 0, we get the hell out of here. But if it's not 0, well, then we'll just write it directly into anchor, because that's where we want anchor to be. And now we can decrement our y, so that, because why can we decrement our y? This is kind of a thing that you can't really do outside of assembly, right? It's kind of an assembly sort of optimization. I just know that the property index for the insertion index is one value smaller than anchor. So once y is set to I anchor, I can decrement y to get it to I index. And sometimes I put a little comment on that just to remind myself that it should be the index, the insertion index. And here we're going to load 0 and stash 0 into there. Okay, so now we've moved the, so now we've put I anchor to the end. We've moved the insertion point to the beginning, and now we're going to, what are we going to do? I think we're just going to jump to del range. That's it, right? Whoops. Jump to del range. I think that's all we need to do. Yeah. So that's short enough, right? So now I'll just count. I mean, again, got a little tiny exception here. It's true, this is a block, and I'm going to make this guy jump to here. But you know what? My mind will tell me when this thing says 20 or 21 or whatever, that 21 is not just this long. I'm going to go, oh yeah, it's designed to jump past both blocks. That's just how I think about it. So let's just count them up. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I guessed that would be 20. That's how often I do this. I looked at that. I was like, that's probably 20. And it is 20. It is 20, not in hex, however. Nasty bug that would be. It's 20 in decimal. Okay. So that should do clear. That should do clear. Alright, let's do the mouse cursor hiding. That'd be cool. Let's save this. This is TKInput.a. So let us do the mouse cursor hiding. This is cool. So TurboMicro Pro has the ability to preview text files while you're looking at your source code. So that's back, exclamation point. And now, to select the file, I have to use an absolute path because of Commodore and CMD DOS. But I've got short paths. So my kernel headers are in OS, the system directory's H directory, and constants and other sorts of things, kernel constants, are in S, the S folder. We're looking for the call in H, so it's a header, and the kernel module is the input kernel module. And it ends in a T. So we can just do that, and lo and behold, I'm now looking at all of the kernel calls and their notes. So here we are. Init mouse, kill the mouse, hide the mouse. There you go. Hide mouse. Turns off mouse cursor. Yeah, that's cool, alright? Hide mouse. So that's easy. It's going to be in the input module, hide mouse. Perfect. So what I do now, and note, I didn't actually change my current working directory, my present working directory. So I'm still in my toolkit source code directory. I just looked up that header file with an absolute path. Okay, so now what I got to do is I need to, I mentioned this in the previous video, but so this class is dynamically loaded and dynamically relocated. And when it's relocated, the entire relocatable gets initialized. It's not the same as creating a new instance of this TKInput class. It's more like it's initializing the relocation process. I can actually show you that. So the very first one that's called is actually a jump to link. Yeah, so link is called because when you relocate this chunk of code, it needs to be linked. I don't know how else to describe it. That's why it's called link, right? It needs to be linked. So in this case, because it's a class, before you load in the class, what you do is you stick a pointer to its superclass into the class pointer, right? So that's what this is saying, is that when link gets called, class should already have a pointer to its superclass. That's how this code knows where its superclass is, by the way, because its superclass could also be a dynamically loaded class. So we load in the first relocatable class, and maybe it subclass is something that's built into Toolkit. But then it gets put somewhere weirdly, somewhere randomly allocated in memory. And then, and of course we figure out where that is, but now we go to load in a subclass of it. We need the subclass of it to know where its superclass is. So we just put a pointer to the superclass into class, and then it turns around and it does this stuff. So init xturn is a very, very low level, it's not even a kernel call. It's something weird that's not quite a kernel call. But it links this relocatable code's externals jump table to the kernel. Even if the kernel's modules move around and change size, this will link the jump table at the bottom, or the externs table at the bottom of this relocatable code. It will link to the kernel. And then the very next thing that it does is it does this class link. And of course the class link links the jump table. Where's the jump table? So the class link will insert the superclass pointer into here, and it will link these JSR jump table entries correctly to the superclass. And then it will take the pointer to this new code, which will actually be not to the beginning of this page, but to here. So it skips that initial link jump, because this TS input is actually the start of the class implementation. Okay. Okay. So it will put a pointer to that back into class. So after the linking is done, put the superclass into class, you call link, or it calls link automatically. And when link returns, the class automatically has a pointer to our new class that's all linked up. And then we can take that, we can then copy the newly loaded class pointer into some other variable or whatever. However you need to keep a reference to it in your application, you just keep a reference to it. Okay. Where was I? Yes. Okay. So what that means is that in order for code in this class to be able to make a kernel call, I have to make one of these relocatable kernel call links. Okay? So I can just put it right here. So I've already got several links to the input kernel module. So I can just slap in another one here. It was hide mouse, right? Yep. So that's really all we need to do. So when are we going to hide the mouse? We are going to hide the mouse basically every single time there's a key press. So we'll jump to our key press label. I mean, yeah, like just think about that. If you cursor, would you want the mouse pointer to disappear? Yeah. If you clicked on the thing, then you hit Command, Commodore A to select all, would you want the cursor to disappear? Yeah. If you type a character, yeah. I mean, maybe the only time you wouldn't really want the mouse pointer to disappear is if you hit return. But that's kind of edgy, right? And it doesn't, I don't think it would cause harm if the mouse pointer was hidden when you hit return. So let's just do it. Let's just hide the mouse. Oops. There we go. And we'll do that before we read the key out of the buffer, because I don't know what hide mouse is going to do to the accumulator. That's probably it. You see, that didn't take much, right? Very, 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 very basic, very, very simple features. All right, let us assemble this. Let's assemble this. TKInput.a. Now, I showed last time sort of a long way to confirm that for relocation that E4 is still available, but you know what? I'm just going to go out on a limb, and I'm going to hope that E4 is still available. So we'll assemble this to that was back 5 to assemble to an object file. TKInput.r. So O, I use O for object files that are not relocated. I use R for object files that are relocated. R for relocated. Oh, yeah. What else have I got on my list of things that I wanted to do? I wanted to implement shift-click to make a selection. Plus I have to do the clipboard. Plus I have to do, what else do I have to do? Clipboard. Right, yeah. I also have to do the mouse, where you use the mouse to drag selections. But, oh god, I don't know. I don't know how I'm gonna do that. I have to study how it works on the Mac first. I know the Mac has a few kind of sophisticated things where, I mean, it's easy if you just want to make a selection within the visible range, right? And that's really easy. Just click. Actually, this is kind of a teaching moment here. Part of the toolkit is that when you click, you have all these nested views, right? So you have a split view, and then inside the split view you've got like a regular view, and then inside the regular view you've got well, let's say a text input, just for fun. So we've got three levels deep. Three things nested inside each other. So if you click on the text field, it's the root view that gets the event first. So in test ground, that'll be the split view. So the split view records on itself the horizontal and vertical coordinates of where the event occurred. Okay? But then that view tries to figure out whether, so for split, for example, it'll figure out, okay, was the event on the splitter, in which case, it may go into a mode of being able to drag the splitter, or was it inside one of my two halves? And if it's inside one of the two halves, then it then forwards the hit test. This is all hit testing. So it then forwards the hit test to whatever child occupies, say, that half. So let's say we click on this half. It'll forward the hit test call, basically just calls hit test, on that child. But then that child then records upon itself the row and column upon which it was clicked. But then that view tries to figure out which of its subviews, which of its nested views, based on the anchoring, would that click have been within. And so let's say that it determines that it was inside, say, the text field, the text input. Okay, so now it's going to call the hit test on the text input. Okay, but now you have a slight complication. This is good, by the way, because the internal contents of the text field could be scrolled. Yeah? So if the contents of the text field are scrolled, say, 5 characters, so 5 characters are off the left-hand side somewhere, well then that view has a scroll left of 5. Okay? So the horizontal click position that gets recorded on that view itself is not the horizontal click of the outer bounds of the field, but it's the horizontal position of the virtual internal contents. This is a 16-bit number, by the way. It's the horizontal position and the vertical position of the virtual internal contents of the field, of the view. And so the internal size is, for this control, it's 1 high, because it's only a single line input. But its width is the length of the string. And so it's if the string has 200 characters in it, its virtual internal dimensions are 200 characters long, and it can be scrolled left and right, in order to see some subset of that virtual space. And so if it's scrolled, say 5 characters to the left, and you click, the click actually records where you clicked in the virtual space of that event, and then that can trickle down. So what's cool about that is that it's already basically a low-level part of the way the hit testing works, that the horizontal position of the event, that's where the insertion point's going to go. So there's like basically no work to be done in terms of clicking on. I can show you actually. It's pretty cool. Let's go to where will it be? Mouse down, I suppose. Yeah. Mouse down. Mouse down. Look at this. It literally pulls the hit column from this, but that's a low-level part of the object. It's this is a property of TKView, two superclasses up from this class. It grabs the hit column, and then it simply checks to see whether the hit column is beyond the end of the string length, because it could be that the field is long and the string is short. So it could be that your hit column is off the end of the string. If that's the case, it just sets the insertion point at the end of the string. But if it's within the string length, the hit column is just immediately assigned as the index and anchor. And that's it. That's it. So it's very, very, very easy. The toolkit does a lot of work for you. Like, that's the whole friggin' point of this system, right? Is that the toolkit makes this shit easy. All right, let's get out of here. All right, if this completely fucks up, I'm going to assume that I didn't put a bug, but that the relocation didn't work properly, in which case I just wasted a little bit of time. I'll have to go back and assemble it to 1000, run the relocator on it, confirm that E4 is still available, and proceed with my life. But certainly seems to have not crapped out, right? Alright, so let's try this. Gregory ASCII is a programmist. Student programmer. Okay? Alright, let's try home first. Oh, home works. Isn't that great? Home works. Okay? Let's try insert. Okay, so insert. Oops. Okay, so insert is now safely being completely ignored. And let's try, look at this. The mouse cursor's gone. Huh, wasn't even paying attention. So here, we'll put the mouse cursor right here. Now we'll hit delete, and there we go, mouse cursor's gone. So that's totally awesome. And now, let's try clear. So we'll hold shift, hit clear, boom. Worked a charm. Isn't that nice? That's just nice, right? This is a string. And then we'll hit clear. Boink. Wonderbar. Wonderbar. And we'll click here. And we'll start typing this. And look, our mouse pointer disappeared. Oh, man, I love that. It feels so Mac-y. God, fucking love that. All right. So let's just check them all off. We are ignoring the insert. We can scratch that. Ignoring the insert. Home moves to the home position. Clear clears the text field. Hiding of the mouse cursor on key presses. Excellent. Left shift and right shift are not working. But of course we have fixed that. Fixed that last night. Just forgot to scratch it off. Alright. What do we got for time? 1:08. Well, let's make that a short video. I think that's been a pretty good, I think that's pretty good. You see, so that was not debugging, that was just adding some features. And I think we can leave it there. Thanks for watching again. See you next time.